Tonight, the tail is wrong. It is too big. On the live feed, dust glows like a wound unstitched. An hour ago, there was restraint in the faint halo. Now it has burst outward, long, open, defiant to geometry. In the control room, no one claps. This is not triumph. They lean closer and do the arithmetic in their heads. The object called 3I Atlas should be a comet. It should obey the sun and the quiet of textbooks. Instead, the tail has swollen past reason. Through thin air and clicking relays, a number lands. Angular length, deprojected, demands a different story. Light pushes dust. The solar wind whips ions straight. We know that. But this plume opens wide, refuses the diagram. Are we looking down the plane of its path, fooled by angle? Or is something in the nucleus shedding faster than models allow? Frames accumulate. The coma brightens, then breathes unevenly, as if winded. A technician reads out values, careful, almost apologetic. Long axis here. Opening angle there. Surface brightness against the background sky, climbing. None of it settles the room. They have seen comets misbehave. They have not seen this. An anti-tail could masquerade as magnitude and reach. If perspective is guilty, the sky will correct us soon. Yet the data keep insisting on excess. A hush moves through the instruments, through the people, through the feed. The narrator voice in your head tries to impose calm. Observe, describe, do not decide too early. But the question has already entered the room, cold and bright. If this does not behave like a comet, what is it? Something from another neighborhood of the galaxy has crossed our street. It is standing under the streetlight now, and the light will not stop growing. Everyone inhales together and waits. At 2:17 in the morning, an alert sounds. A point of light jumps across 3 frames, too quick for a background asteroid, too clean for noise. In the control room, chairs stop creaking, people lean toward the monitors and hold their breath. The asteroid terrestrial impact last alert system pipeline checks the usual culprits. High-orbit satellites, sensor ghosts, variable stars that seem to move when seeing wobbles. One by one, the false answers fall away. The object stays. A junior analyst links tracklets from 2 stations an ocean apart. The next night's predicted position is chalked on the board. It is a small box, a dare to the sky. If the box is right, the target will be there. Night 2 cooperates. The box is good. The halo looks barely swollen, a whisper of a coma. The measured place on the sky sits where last night's fit said it should. Residuals shrink. Confidence grows, but slowly. Coordinates, times, and brightness go to the minor planet center. A preliminary designation returns with the usual call for help. Across longitudes, amateurs and professionals swing glass toward the forecast patch. More points land in the ledger. A larger mirror confirms a faint coma. The orbit solver tilts. Eccentricity climbs above 1 and stays there. Someone writes the number in a notebook and circles it twice. The room goes quiet in a way that does not feel like silence. This one is from away. The name updates. 3rd interstellar object, discovered by the survey, now called 3I Atlas, also given a comet designation for bookkeeping. Geometry notes follow. The path will hug the sun. The Earth will watch from a safe distance, off to the side. The question lingers like a thread. Under that geometry, how strange will the tail appear? You think you know a comet's tail. You do not know this one. Start with the 3 numbers that matter tonight. Angular length, opening angle, position angle from the sun. They are big, they are growing, and they do not quite agree with the diagrams. In textbooks, there are 2 engines. Ions, ripped from gas, race down the solar wind and draw a straight blade away from the sun. Dust, pushed by radiation pressure, curves gently, each grain responding with a beta all its own. 2 tails, one straight, one arcing, simple until it is not. They measure, not marvel. A narrow cut across the image yields a surface brightness profile. Thresholds fix the edge. Stars are masked, satellite streaks rejected, faint clouds noted. The coma is subtracted. What remains is the thing we must name. Deprojection comes next. Distance and phase angle convert arc minutes into kilometers. Uncertainties multiply: thickness along the line of sight, tilt of the tail axis, the fact that sky is a liar at low phase. Still, the number is large. Anti-tail enters like a defense attorney, view along the orbital plane, and old dust lines up, making a bright spike that seems to point sunward. It can mimic size. It can confuse the eye. If this is only perspective, the position angle should rotate predictably night to night. It does not enough. They overlay syndines, families of grains with one beta. Then synchronies, sheets of dust released at one time. The fits slide off the light. The opening angle expands faster than mass loss models prefer. Knots appear, then fade. They hunt noise. They find none that can carry this far. So the tail stands there, oversized and incorrect, and the question turns inward. What mix of materials could bend behavior this way? Comets are not dirty snowballs. They are disciplined leaks under relentless sunlight. A nucleus, small, dark, and astonishingly porous, warms. Ice wakes. Gas carries dust. Jets begin quietly. Beneath a crust, water ice, carbon dioxide, carbon monoxide, and ammonia sit among silicates and complex organics. Heat seeps downward. Pressure rises along fractures. When a crack reaches daylight, a fountain starts, and a rotating world spirals into the coma. The coma is the breathing space around the nucleus. Density falls with distance. Observers track surface brightness, which often declines near inversely with radius. From that slope, they infer how fast fresh gas and dust are made, and how quickly they fade or fragment. Two tails issue from this engine. The ion tail forms when molecules lose electrons and become captive to the interplanetary magnetic field carried by the solar wind. It points almost directly away from the sun and can kink when a solar storm sweeps through. The dust tail bends. Radiation pressure pushes grains while gravity holds them back. Each grain responds with its own beta parameter, a measure of how sunlight competes with mass. Families of equal beta trace lines called syndines. Grains released at one moment sketch sheets called synchrons. Spectra identify the mixture. Hydroxyl betrays water. Diatomic carbon glows green. Cyanogen and triatomic carbon add structure. In infrared light, carbon dioxide and carbon monoxide announce themselves. Non-gravitational forces appear as tiny drifts in the orbit. Asymmetric jets give the nucleus a shove and a twist. Spin states change. Seasons of activity reveal themselves in repeating swings. The standard picture is tight: straight ions, curved dust, rotating geometry that explains the night-to-night changes. Outbursts exist but fit a playbook. Then comes an object that refuses the playbook. So what precisely still defines a comet? If this tale is right, the textbooks are wrong. If the textbooks are right, this tale is something else. Geometry says one thing, the sky says another. The fear enters with the data. A comet has a checklist, a breathing coma, an ion tail that points away from the sun, a dust tail that bends, spectral lines from hydroxyl, diatomic carbon, and cyanogen. Small, non-gravitational drifts from uneven jets, a spin state that changes with season. First hypothesis: composition. Suppose carbon dioxide or carbon monoxide dominates, while the usual carbon-bearing emitters are weak. That mix could widen the plume and speed its growth. Tests are direct. Optical spectra for fingerprints, infrared for the heat of fresh ice and gas. Second hypothesis: structure. A large, quiet nucleus lies under a desiccated crust. A fracture opens, a buried layer races to space. Short, violent outbursts follow. Tests are dynamical. Shifts in rotation period, torque on the pole, an asymmetric light curve. Third hypothesis: no reliance on sublimation. Electrostatic lofting can lift fine grains. Thermal cracking can fling shards. Photodesorption can free molecules. Fluorescence can exaggerate apparent size. Tests compare grain sizes, polarization, and filaments. Fourth hypothesis: extreme circumstance. Viewing geometry stacks old dust into an anti-tail. A coronal mass ejection scours the ion tail and fakes a surge. Tests demand night-to-night rotation of the position angle and a disconnection event, or else it is not a comet. To say that fingerprints must be missing across bands. So we set rules, fit syndines and synchrones, measure beta parameter, correct the light curve for phase, solve for accelerations along 3 axes. Better to break an idea than to bend evidence. Memory holds a cautionary case. Once, a visitor broke rules and split the room. Shall we open that file? Autumn of 2017. A strange streak crossed the neighborhood and the room went quiet. The orbit solved above 1. A new name followed. 1I, Oumuamua. The finder marked the nights left to watch on the whiteboard. There would not be many. Early data were crisp and cruel. No clear coma, no tail to comfort the modelers. The light curve swung wildly, as if a stretched shard or a flattened flake were tumbling in irregular sunlight. Spin state estimates refused to agree. The object did not care. Then the small drift appeared. The track on the sky missed gravity by a little and kept missing in the same way. Non-gravitational acceleration, persistent and real, entered the fit. Traditional jet models needed gas and dust that telescopes could not see. Materials were summoned. Pure hydrogen ice that sublimates without leaving color. A slab of nitrogen carved from the face of a distant dwarf planet. A featherweight clump of dust with vast porosity, so light that sunlight could shove it without much heat. Each offered hope. Each cost plausibility. Mechanisms were summoned. Thermal cracking, photodesorption, fluorescence that amplifies without mass. Could a gentle push hide in plain sight? Midway through the debate, another possibility arrived and split the room. A thin sheet driven by radiation pressure, a sail perhaps even made, not grown. The pause was long, then the work continued. Predictions were written where they could be tested. The hunt for evidence resumed. Limitations mattered. The window was short. The phase angle was unkind. Signal settled near the noise floor. Temptation to fill gaps had to be resisted. Method remained. Solve for 3 components of acceleration. Compare models. Tie geometry to the light curve. Let data ruin favorite ideas first. That file ends in humility. It opens ours. Another interstellar visitor, but this one behaved by the book. 2. Borisov arrived trailing comfort. A bright coma, 2 tails. The ion blade pointed away from the sun. The dust fan curved, obedient to radiation pressure. Geometry rotated, and the position angle followed like a metronome. There was time to watch. The window stretched across months, not days. Photometry settled into a rhythm that models could hum along with. After calibration, the surface brightness fell close to the classic slope. Masks removed the stars. The coma remained busy and ordinary. Spectra spoke. Hydroxyl said water. Diatomic carbon painted the familiar green. Cyanogen added its teeth. In infrared, carbon dioxide was present, but carbon monoxide shouted louder than expected, a clue to a colder nursery or a shorter childhood in sunlight. Dynamics were polite. Non-gravitational terms A1, A2 and A3 were small and steady, consistent with patchy jets. The spin period drifted in step with season, as active regions turned toward and away from light. Nothing demanded exotic physics. Nothing refused the playbook. Midway to perihelion, a hiccup. Knots appeared in the dust tail. Large grains parted company and slid outward on lazy arcs. For a night it looked like trouble. Then it looked like a comet having a normal bad day. Continuity returned. The diagnostics even improved. Borisov then was a baseline. Interstellar, yes, but textbook. Its chemistry differed in interesting ways, rich in carbon monoxide, poor in long carbon chains, yet its behavior anchored the discipline. When data are generous, simple models win. When models fit, imagination rests. Place the files side by side. Oumuamua broke rules and humility grew. Borisov kept rules and theory exhaled. Where does 3I Atlas sit on that line? Its tail has already voted with excess. Which way does the needle swing now? On paper, the path screams interstellar, but the geometry whispers a no-show for Earth. The orbit is hyperbolic, the excess speed stays positive, the inbound and outbound lines tilt away from the ecliptic. Gravity cannot keep this traveler. Perihelion falls near solar conjunction, elongation shrinks. The ground-based window becomes a slit at dawn and dusk, where glare and low altitude cut signal and seed mirages. The survey stretches, yet the view is poor. Closest approach to Earth remains far, a comfort measured in hundreds of millions of kilometers. That distance protects lives and confounds cameras. Weak contrast, crowded stars and thin clouds conspire to paint a tail longer than it is. Phase angle grows, and with it forward scattering. Dust grains catch sunlight and throw it toward us, making the fan look brighter and broader without demanding huge mass loss. Geometry can perform a magic trick that physics never ordered. Expect rotation of the tail's position angle night to night. If the tail is honest, it will follow the changing sun object Earth triangle. If it does not, some other engine is steering the light and dust. Deprojection tries to tell the truth. Observers turn arc minutes into kilometers using distance and phase. Uncertainties pile up. The thickness along the line of sight, the tilt of the tail, the fact that low phase angles lie. Photometry wants fairness. Phase corrections allow one night to speak to the next. A rising curve after correction signals new material or new heat. A flat curve says geometry alone is guilty. Mid-hook, the model predicts an obedient swivel. The images hedge, the angles drift, but not enough. Something else is pressing down on the chalkboard drawing. What presses? Solar weather waits off stage, armed with wind and field, ready to touch the tail. Comet tails do not only answer to ice, they answer to weather, solar weather. A supersonic wind streams from the sun, carrying the interplanetary magnetic field like invisible wire. Ion tails hitch to those wires. A small change in flow can twist them. A large change can break them. Coronal mass ejections are the blunt instruments. A shock front arrives first, density and field jump. The tail brightens in patches, kinks, and sometimes tears free. Behind the comet, reconnection stitches a new tail that grows in minutes to hours. There are subtler sculptors. Corrotating interaction regions sweep around like rotating fences, compressing plasma and reorienting field lines. Sector boundaries flip polarity. Rays appear, narrow and literal, along the field. All of this is motion the nucleus never makes, yet the tail performs. Timing is the test. Solar wind speeds span 300 to 800 kilometers per second. One can forecast an arrival by propagating measurements outward and then along the comet's heliocentric distance. If a morphology change lands on schedule, the culprit is weather, not ice. Midway through a watch, a fold races down the tail of 3I Atlas. Brightness crests, then collapses. A wedge detaches and drifts away, faint and obedient to the wind. For a while, the comet looks wounded. Then a fresh blade sharpens, aligned to the new field. Geometry can still mislead. Low elongation inflates the fan through forward scattering. An anti-tail can masquerade as size. But geometry turns smoothly night to night. Weather does not. It jumps. Apply the checklist. Kinked structure. Disconnection event. Rays along the field. A phase lag that matches a calculated solar wind transit. If those appear together, the tail has been edited by space, not by the nucleus. Then test again and let repetition convict the culprit. Green is a promise and a trap. Around many comets, the coma glows green while the tail does not. Gas makes the color, dust steals it. Tonight, with 3I Atlas, the color story feels wrong, or at least incomplete. Observers separate light into two families. Emission from gas draws narrow lines. Continuum from dust is broad, slightly red, and often stronger in the tail. Diatomic carbon, excited by sunlight, paints the coma green. Cyanogen adds violet structure. Hydroxyl betrays water, fragmenting under ultraviolet glare. When those signatures are strong, a comet behaves like the book. Now the puzzle. The fan looks wide, perhaps too wide, yet the classic green is shy. Mid-hook. If the green is missing, what is lighting the tail? Two paths lead forward. Path 1. The ice mix is cold and unusual. Carbon dioxide and carbon monoxide dominate, driving jets without feeding much diatomic carbon or cyanogen. In infrared light, those ices advertise themselves clearly. If they lead, the tail can grow fast even while the green stays faint. Path 2. The grains are small and bright. Fine dust fluoresces and forward scatters, inflating apparent size. Polarization along the tail will reveal the trick. The test bench is simple and strict. Take spectra across the coma and down the tail. Look for hydroxyl, for the sodium doublet, for forbidden oxygen lines in green and red. Map line to continuum ratios. Use standard narrowband filters tuned to cyanogen, diatomic carbon, triatomic carbon, ionized carbon monoxide, and amidogen. In parallel, record polarization to estimate grain sizes and alignments. Calibrate carefully to avoid thin cloud and background stars. If gas dominates, the colors will sharpen into lines. If dust dominates, the continuum will flatten and the green will fade. Either way, composition steps out from behind the light. You cannot see the nucleus, you see the breath around it. To know its size, you must peel the glow away and listen for what survives subtraction. Start with optics. Fit a point spread function at the core and remove the coma's slope. What remains, if anything, is the unresolved nucleus. Background stars and thin cloud lie. They fatten the core and exaggerate size. Discipline means smaller apertures and cleaner frames. Assumptions ride every estimate. Albedo, phase function, shape, change any, and kilometers move. A round model is a convenience, not a truth. Report a range, not a single number. Keep humility to every digit. Dust confuses everything. AF-RHO measures coma contribution. High AF-RHO inflates total light and makes a small nucleus look large. Use dual component models for the coma. Isolate grains from the core, or concede you cannot. Thermal infrared tries a different door. Warm surfaces radiate. Fit a thermal model and infer diameter without caring about reflectivity. But hot dust radiates too. Separate bands. Cross-check color temperatures. Refuse easy answers. Dynamics speak quietly. Non-gravitational accelerations, the A terms, reveal thrust from jets. If the A's are tiny, the nucleus may be large or merely quiet. If the A's are big without matching gas, the model is wrong or the mechanism is different. Light curves help. Amplitude suggests shape. Period tracks torque. But dust can modulate brightness and impersonate a stretched body. Outbursts hide rotation and bloat radii overnight. Midway truth. If the nucleus disappears inside the coma, you might be measuring only dust. Wait for steady nights. And then measure again. Trust only acquire. High-resolution images, infrared, polarization, and orbital fits must agree. If they do, the diameter means something. If they do not, the number is noise in a glowing room. If it is not a comet, what is it? The investigation opens 4 branches, and each must answer with evidence, not style. Branch 1. Exotic ices held cold. Suppose carbon dioxide or carbon monoxide dominates while carbon-bearing emitters are weak. Jets run, but classic green lines stay faint. Expect a wide fan and brisk growth. Test with thermal infrared and high-resolution spectroscopy across the coma and down the tail. Branch 2. Fluffy dust with enormous area. Imagine fractal aggregates, feather-light and easily pushed. Radiation pressure wins. Beta values rise. A modest mass looks loud. Expect high polarization, a strong phase slope, and a slightly reddened continuum. Test with imaging polarimetry and color gradients. Branch 3. Thin sheets driven by light. A membrane, natural or engineered, would couple hard to photons and soft to gas. Non-gravitational acceleration should point sunward and scale nearly with the inverse square of distance. Expect little gas, strong pressure effects. Test with precise orbit fits and day-by-day residuals. Branch 4. No sublimation required. Electrostatic lofting lifts fines. Photodesorption frees molecules. Thermal fracturing sprays shards on the day-night boundary. Expect erratic filaments, very small grains, and weak gas lines. Test with polarization, grain size modeling, and time-resolved imaging. Mid-hook, the tail can be an exaggeration of light, not an outpouring of mass. To prove that, standard gas fingerprints must be absent repeatedly under good conditions. Matrix of tests. Narrowband filters for cyanogen, diatomic and triatomic carbon, ionized carbon monoxide, and amidogen, hydroxyl and sodium lines, thermal bands for carbon dioxide and carbon monoxide, phase-corrected light curves, Sindine synchrone fits, A1, A2 and A3 accelerations, rotation and torque solutions. One rule governs all branches: predictions first, then failure if the sky disagrees. The clock is already running. Who will keep watch across bands and hours while the tale keeps changing? To learn what 3i Atlas is, one must first know who is watching. The network spans Earth, near-Sun sentinels, and the red hills above Mars. Coverage, cadence, and redundancy matter. Coordination across hemispheres keeps gaps from opening wide. On the ground, surveys keep the object in the ledger. Atlas, Pan-STARRS, and ZTF mark positions and brightness. Large mirrors take over. Gemini South, VLT, Subaru, and SOAR resolve the tail's shape, measure opening angle hourly, and freeze knots before they smear. Spectrographs open a drawer. Medium and high dispersion instruments walk slits from coma to tail, separating narrow gas lines from dusty continuum. Imaging polarimeters weigh grain sizes and alignments. Color cameras track reddening that hints at composition and phase. SOHO and stereo see ion tails kink and tear in real time. Solar orbiter gives context for field direction and solar wind speed. When a coronal mass ejection launches, clocks start. The team propagates the shock to the comet's distance, then waits for a matching change. Parker Solar Probe samples the flow from inside the furnace. Density, speed, and field angle feed models that predict what the tail should do hours later. If the prediction lands on the image, weather, not ice, wrote the script. Mid-hook, what will eyes on Mars see? At Mars, Maven reads plasma and field from a vantage Earth cannot share. MRO can image at a different phase angle, shrinking, forward, scattering illusions. Second geometry checks the first, and an independent clock times the same storm from another side. Shifts handoff across longitudes, north and south trade night. A soft alert triggers when the position angle drifts beyond forecast. Data flow through a simple gate. 2 bands, 2 telescopes, 2 nights before the adjectives arrive. When the instruments sing in tune, the tale will name itself. One tale can scare you, one number can calm you. The image races across your feed, bright and long, scored with urgent music. It looks like a threat, it is not. Start with distance, 3. Atlas will pass far from Earth, hundreds of millions of kilometers far. Start with geometry. The path slips behind the sun, then away. Start with energy. Hyperbolic speed means it will not stay. Hype thrives on scale bars missing and frames sped up. Time-lapse stretches minutes into drama and turns a gentle fan into a flood. Cropped fields erase stars that would show how faint the glow really is. The picture sells a feeling, numbers sell the truth. Mid-hook, the headline says, coming straight at us. Breathe, slow, check 3 facts. Minimum distance. Elongation on the night in question, sign of the orbital energy. If any are dull, the threat is gone. There are 2 kinds of risk. Physical risk is impact, radiation, or dust thick enough to harm. None apply here. Perception risk is noise that drowns out method, that one always applies. Cure it with source, context, and timestamp. If you want to look, do it right. Twilight edges, a small binocular, short exposures on a tripod, note tail position angle, opening angle, and background brightness. Write it down. Compare tomorrow. Use a simple checklist. 2 independent sources. 2 nights. 2 bands if possible. Do not conclude from one spectacular frame. Favor teams that publish raw data and calibrations. Learn the weather marks, kinks, rays, disconnection events. Those point to solar storms, not malice. Anti-tails rotate smoothly with geometry. That is how you know the difference. When fear cools, curiosity sharpens. Then the big question returns. What does 3i Atlas reveal about the place it was born? Meaning does not sit on the photograph. It lives in the models we revise. 3i Atlas matters because frame by frame it pressures theory. Planet formation is a story of leftovers. Interstellar visitors are pages torn from protoplanetary books. They're chemistry tests where cold worlds start, how they migrate, and which ices survive first light. If 3i Atlas tilts toward carbon monoxide and carbon dioxide, that tilt fingerprints its nursery. Volatile budgets are ledgers. Ratios among water, carbon dioxide, carbon monoxide, and ammonia mark a thermal history. Diversity among visitors implies a galaxy that mixes laboratories more than it mirrors them. The tail is also a plasma experiment. Solar wind and magnetic field right on it like an oscilloscope trace. Kinks, rays and disconnections timestamp storms we cannot measure everywhere. The comet turns weather into a ruler. A new survey era arrives. Rubin, NEO surveyor, and polarimeters promise more visitors seen earlier with clearer context. 3i Atlas is the rehearsal. It tests cadence, alerts, and the rule that raw data outrank adjectives. The lesson is not what it is, but how we know. Predict, then verify. Let models fail in public. Say unknown on Thursday and update on Friday. Trust cross-band choirs over single frames. Reward forecasts that can be wrong. There is biology at the edge. Debris ferries organics and ice between suns. Delivery is not destiny, but it keeps the door open for testable prebiotic chemistry. There is culture too. Fear yields to curiosity when process is transparent. Viewers become investigators, not customers. Confidence grows when the sky speaks in numbers, not slogans. So the photograph steps back and the method steps forward. 3i Atlas will pass on, but the discipline it sharpened remains. We choose the universe we can check, and we keep watching.